Yes, sir.
Okay, good.
Yes, sir.
Guys, please come on time. Come on time. 9 o'clock. Okay. So, guys, I'm going to start problems. So, before starting problems, I'm going to cover a little bit of theory, that is efficiency of a joint. Okay. Oh, God. So, people are coming late. Okay, efficiency of a joint. So the efficiency of a joint eta is given by strength of joint per pitch length divided by strength of solid plate per pitch length multiplied by 100. So that is a formula you remember. So I'm not going to go into the theory completely. Okay. So once we start solving the problems, you'll understand what it is. Okay, that is the best way this can be explained. Okay. So before starting problems, what I do is I will go back to the previous page, that is page 3, to explain about the connections. So if you look here, so this is a bolt. So this is the shank area where the area of cross section does not get reduced as a result of the thread. Okay, area of cross section is given by pi by 4 d square. Okay, so when you come to this part, this is called the threaded area. Here the area of cross section gets reduced. So what is the area of cross section in the threaded area? That is pi by 4 d square multiplied by 0.78. So as a result of the thread, okay, the area of cross section gets reduced. So in some of the bolts, you see the bolts threaded throughout the length. So in that case also, the area of cross section is given by 0.78 times pi by 4 d square. Okay, coming to this. So this is a joint. 1 second. So this is a lap joint. This is one member and this is the other member. We are putting one plate over the other plate. Okay, and we are trying to connect. Okay, and we are connecting through bolts. So depending on the design, we may need more than one bolt. Okay, 2, 3, 4, 5, 6, etc. So when you look from the top, you see the number of bolts. So when you take a cross section, you'll see only one bolt. So for a moment, you forget this insulating gasket. Okay, and also the steel washer. Think that, so these two plates are in contact, and think that these two plates are subjected to a tensile force of P, for example. So when you apply tensile force here, so there is going to be another tensile force of the same magnitude, say P. Okay, once you pull it, so this side of the bolt gets in contact with this side of the plate. Similarly, when you come here, this side of the bolt gets in contact with this side of the plate. So that is diagonally opposite sides get in touch with or come in contact with the bolt and the plate. So instead, if you apply compressive force, it is opposite. So this side of the bolt gets in contact with this side of the plate. Here, again, this side of the bolt gets in contact with this side of the plate when you apply compressive force. So whether we are designing a connection for a compressive force or a tensile force, it doesn't matter. Okay, the design does not change. The design of connection does not change, and only the magnitude of the force matters. Okay, 1 second. Anusha, you'll have to come on time. Otherwise, beyond 9:05, I'm not going to let anybody in. Okay, so coming to this again. So this type of connection is called bearing type connection. Bearing type because one face of the bolt bears against another opposite face of the plate. Okay, that is bearing. Okay, when we come here, there are two ways a bolt can fail. Say bolt can fail along this surface. This is called the shear surface, because there is only one failure plane of this bolt. So this bolt is in single shear. Remember, this bolt is in single shear because if at all a bolt fails by shear, it fails along only one plane. Okay, so which area should be considered when we are designing or when we are checking for single shear? So whether you need to consider the threaded area or the bolted area, that depends on the length of the thread. Say, assume that the thread is extended throughout the length of the bolt. Then whatever the shear plane is passing through the threaded area. Then at the threaded area, as I said before, the area of cross section of the bolt is pi by 4 d square multiplied by 0.78, because we are going to multiply by 0.78 to reduce the area of cross section of the bolt as a result of the thread. Okay, so sometimes what happens is the thread will be spread over certain length. When it comes to the shear plane, it is going to fail along the shank area. So in this case, in the case of the shank, so the area of cross section of the shear plane is simply pi by 4 d square. Is it clear to you? One second. Okay, with that, I'm going to go and solve a problem. So I hope you have the code book with you, all of you. So just I'm going to tell you open a specific page number. So please open it. Okay, before going, there is one more point I need to clarify. So bolt sizes. See, if you look here, the bolts are available from 5 to 36 millimeter in diameter and are designed as, they are designated as M5 to M36. M5 bolt, M10 bolt, M12, M16, M20 bolt means M20 means 20 millimeter diameter bolt. So 20 stands for the diameter of the shank, but not the thread area. Okay. So going further, I'm going to take up a problem. One second. So guys, please, next to the USN number, add your names. So 4MH 18CV075. So it is not done. Okay, coming to the problem. So the problem says calculate the strength of a 20 millimeter dia bolt of grade 4.6 for the following cases. So the main plates to be jointed are 12 mm thick. The plates are made of steel of grade Fe415. Okay, there are three kinds of joints. One is a lap joint. So the other is single cover butt joint. The cover plates being 10 millimeter thick. So, and the next one is double cover butt joint, each of the cover plate being 8 mm thick. So there are three cases. See, if you understand this problem, then the design of bolted connection is going to be very easy for you to understand. So let me reject this guy. So it is already late by 15 minutes. Okay. So let us take up the first case. It says calculate the strength of a 20 millimeter diameter bolt. Look here. So there is only one bolt, but in reality you are not going to provide just one bolt. Okay, you have to provide at least 2 bolts in any joint, and of course more depending on the design requirements. Okay, so just to make you understand the concept of the bearing type of connection, this is a bearing type of connection. So only one bolt is taken, and once you understand the concept, then we can go further and increase the difficulty of the problems. Okay, so here, 1 second, just 20 millimeter diameter bolt of grade 4.6. So what is the grade of the bolt? It is 4.6. That means this is ordinary bolt or black bolt or rough bolt. So what is the ultimate tensile strength of this bolt? The ultimate tensile strength of this bolt is 4 multiplied by 100, that is 400 Newton per millimeter square. Then what is the strength of the plate? The strength of the plate is 410. Fu 415 means 410 Newton per millimeter square. That is the ultimate tensile strength of the plate. So what is the thickness of the plate? That is 12 mm thick. Okay. So here are the details I have written. So for Fe 410 grade of steel plate, so characteristic tensile strength of plate material Fu, that is represented by Fu equal to 410 Newton per millimeter square. So for bolt of grade 4.6, so characteristic ultimate strength of the bolt, that is represented by FUB. So where B stands for bolt, that is equal to 400 Newton per millimeter square. Okay. So then gamma MB, that is a partial safety factor for the bolt. So this value 1.25 we are going to obtain from table 5, page 30 of the code book. Okay. So whenever you solve a problem in the examination or in internals or assignment, so you don't have to write table 5, page 30, etc., etc. Just we don't need that. So whatever I have written here is purely for your reference. Okay, so that when you are studying, so it will be easy for you to understand. Next comes net tensile area of 20 millimeter diameter bolt. A and B equal to net. N stands for net, B stands for bolt, is equal to 245 millimeters square. See, here for 20 millimeter diameter bolt, the area of cross section is pi by 4 d square, that is d equal to 20. That is going to be equal to 314 millimeter square is the area of cross section of 20 millimeter diameter bolt. So by assuming that the shear plane passes through the threaded area, we have to multiply that area by 0.78. Once you multiply that area by 0.78, that becomes the net area, that is equal to 245 millimeters square. So look here, these two are the plates. This is a lap joint. Lap joint means one plate is coming over the other. So we don't know how long or how far the thread is extended in the bolt. So simply on safer side, what we are going to assume is the thread is extended throughout the length of the bolt. That way, if at all the bolt fades due to shear, the shear plane or the failure plane in shear is going to pass through the threaded area. Okay, so the area of cross section of the bolt at the threaded area is equal to 245 millimeters square. Okay, so let us take the first part. First case, lap joint. This is the lap joint. Okay, so when you pull it, okay, so this surface bears against, that is the surface of this bolt, this side's surface of this bolt is going to come in contact with this surface of the plate. So that's why it is called bearing type connection, because one is pushing over the other. Okay. Similarly, if I take this, so this side is going to be in contact with each other. Okay. And this is the shear plane. So there are two possible ways a bolt can fail. One is through shear and the other is through bearing. So that is whenever a bolt comes in contact with the plate, pressing against each other, some material has to yield first, is it not? So when two materials of different strengths are pressing against each other, which material yields first or fails first? The material having less strength is going to yield first. So here, what is the bolt strength? 400 Newton per millimeter square. So what is the plate strength? 410 Newton per millimeter square. So the plate is little bit stronger than the strength of the bolt. So if at all the yielding happens for the bolt as the strength is less than that of the plate. So we need to consider and we need to find out what is the strength of the bolt in shear and also what is the strength of the bolt in bearing. So we'll have two values, and once you find out those two values, take lesser of those two values as the bolt strength. Okay, 1 second. Okay, so coming to this first, that is lap joint. Guys, I'm going to go very slowly because this is the first problem. If you understand this, so design of bolted connection, or if you don't understand this, then it will be very difficult for you guys. Okay, so let us consider this. So open page number 75 of the code book. Please open page number 75 of the code book. Okay, if you open it, in the first column of page 75, you'll see 10.3.3 shear capacity of bolt. Do you see that? So you'll see the formula VDSB equal to VNSB divided by gamma MB. Is it not? So then what is V? We need to find out VDSB. That is the capacity of the bolt or the shear capacity of the bolt. Okay. So then gamma MB is 1.25. We got that value from the table on page 30. Okay. So VNSB is given by, if you go down a little bit on the same page, it is given as VNSB equal to FU by root 3 multiplied by NN ANB plus NS ASB. So I have written those two formulas here in the notes. So if you look VD on the notes, so VDSB, so where D stands for design, S stands for shear, B stands for bolt. That means that is the design shear strength of the bolt. Okay. So VNSB, N stands for nominal, and S shear and B for bolt. Once you divide this nominal shear strength of the bolt by partial safety factor of gamma MB, which is equal to 1.25, you are going to get the design shear strength of the bolt. So coming further down, so whatever VNSB value I've substituted here. So gamma MB is here. So where did I get this? Again, under 10.3.3, page 75 of the code book. So we get VNSB equal to this much. Then what is FU by root 3? So FU is the ultimate tensile strength of the bolt. Once you divide that ultimate tensile strength by root 3, you are going to get the ultimate shear strength of the bolt. Shear strength of the bolt is always measured per unit area. Okay, per unit area of the bolt along the shear plane. So if I go up, look here, if at all the bolt fails due to shear, this is the shear plane. Okay, you need to find out the shear strength of the bolt, okay, by multiplying the shear stress by the net area of the bolt. Okay, so coming here, this gives the shear strength of the bolt, that is FU by root 3 multiplied by NN ANB plus NS ASB. NN is the number of net areas, A and B, where N stands for net, B stands for the bolt. Net area of the bolt multiplied by number of surfaces plus NS, that is S stands for shank. Okay, area of cross section of the shank, and B stands for the bolt. Okay, so here this does not arise. This is equal to 0. The reason is we assume that the shear plane is passing through the threaded area. Okay, and there is only one shear plane. That's why this ns becomes 0. Once ns becomes 0, the whole thing will become 0 automatically. Coming to nn, a and b. So what is nn? Nn equal to 1 because there is only one shear plane. That means there is only one shear plane. That means the bolt is in single shear. Okay, when the bolt is in single shear, nn equal to 1. So A and B is the net area of the bolt. That is 245. How did we get that? Pi by 4 multiplied by 20 square, where 20 is the diameter of the bolt, multiplied by 0.78. Why did we multiply that value by 0.78? Because the shear plane is passing through the thread, where we get the reduced area of cross section. So once you do this, I got this value, that is the shear strength of the bolt value equal to 45,264 Newton. So once you convert that value into kilonewton, so we are going to get that value equal to 45.26 kilonewton. That is the bolt value in shear. Okay, so that means design value of the bolt in shear, or you can call that as bolt value in shear. Okay, that is one way it can fail. If at all the bolt fails due to shear, it fails at the value equal to 45.26 kilonewton. So there is another way. Okay, a bolt can fail. That is through bearing, because when you pull this area of contact, okay, gets, due to the contact, the material gets, it fails or yields. Similarly on this side. So we need to find out what is the bearing strength. Okay. So we need to get what is the bearing strength. Again, go to page number 75, go to 10.3.4 in the second column. Okay, are you on that page, page 75? 10.3.4 in the second column, it says bearing capacity of the bolt. So the formula says VDPB equal to VNPB divided by gamma MB. So what is VNPB? VNPB equal to 2.5 kb dt Fu. That is there, just below that line. So gamma MB equal to 1.25. You got this value from table 5 on page 30 of the code book. Okay. Next, so we need to find out what is VDPB. To find out VDPB, we need to find out what is VNPB. So to find out VNPB equal to 2.5 kb dt Fu. So in this case, so kb we need to find out. D is the diameter of the bolt. T is the thickness of the plate. Fu is the bearing strength of the plate or the bolt, whichever is less. Okay. So coming to this, finding out kb, again, if you look at the code book, so below that line you just now referred, kb is smaller of the four values. It gives E by 3DO, comma, P divided by 3DO minus of 0.25. Next, FUB divided by FU, comma, 1.0. So we have four values of KB. Okay. So out of those four values, take the least value as the KB value. Okay. That value should be substituted here in the formula to get VDPB value. Then coming to KB, what is E? E is nothing but the end distance. So end distance is 1.7 times DO, where DO is the diameter of the bolt hole. Okay, 1 second. So DO is the diameter of the bolt hole. So E minimum is 1.5 DO or 1.7 times DO. Okay, so whether we take 1.5 DO or 1.7 times DO depends on the edge condition of this plate. Here, what is the edge condition? If it is a rough edge, okay, we need to take 1.7 times DO as the end distance. Okay, here what I do is I'm going to assume this surface as smooth. That means this end is machine cut. So once that is assumed as machine cut, this has a definite edge. That way we can take this end distance as 1.5 times DO, where DO is the diameter of the bolt hole. Okay, so coming to this, E minimum. So E minimum is, as I said, 1.5 times DO. This is as per 10.2.4.2. So where DO equal to diameter of the bolt hole, that is given by diameter of the bolt, which is 20 millimeter plus 2. Where did I get this 2? If you go to page number 73, please go to page number 73. The kind of bolt we are using is 20 millimeter. So it falls between 16 and 22 millimeter. Okay. So corresponding clearance for 20 millimeter diameter bolt is 2 millimeter. So 2 plus 20 plus 2 is 22 millimeter. That is the diameter of the bolt hole. That's what I have taken here. Okay. So coming to this, once E minimum is found out, we need to go for E maximum. E maximum again on page 74 of the code book under 12.2.4.3, it says 12 times T epsilon, where epsilon equal to 250 divided by Fy under root sign. If you go to page number 74 under 10.2.43, first column, go to the end. It gives E maximum value, that is the maximum end distance you can give, that is 12 times T times E epsilon, sorry. So in this case epsilon becomes 1. The reason epsilon becomes 1 is Fy equal to 250 Newton per millimeter square for Fe 410 plate. Okay, so that way E maximum is 12 times T epsilon. T is the thickness of the plate. It says thickness of the thinner plate. Okay, so in this case we have two plates of the same thickness, 12 millimeter and 12 millimeter. So in this case we have to take 12 millimeter as the thickness of the plate, and epsilon is 1. So E maximum is 144 millimeter. What it means is E minimum is 33 millimeter and E maximum is 144 millimeter. So that means you can give an end distance from the center of the bolt to the edge a minimum of 33 millimeter. Okay, 33, and a maximum of 144 millimeter, and any value in between is okay. Okay, so if I come here, therefore we shall give an edge distance equal to 33 millimeter. If you want, you can give 35 millimeter, 40 millimeter, as long as the value is between E minimum and E maximum. Okay, that is the end distance. Similarly, we need to go for the pitch. So minimum pitch, what is minimum pitch? 2.5 times the diameter of the bolt. Remember, this is not the diameter of the bolt hole, it is the diameter of the bolt. Where did I get this 2.5D? Again, go to page number 73. Go to page number 73 under 10.2.2, second column at the end of the page. It says, I'm going to read out, the distance between center of fasteners shall not be less than 2.5 times the nominal diameter of the fastener. Here fastener is nothing but bolt. Okay. So here diameter of the bolt is 20. 2.5 times 20 is 50 millimeter. So that is the P minimum. That is the minimum pitch you need to give. Okay. So what is P maximum? So as per 10.2.3.2, P maximum should not exceed the following two values. 16 times the thickness of the thinner plate, 16 times 12 is the thickness of the plate, and also it should not exceed 200 millimeter. So I have got two values, 192 and 200 millimeter. So P maximum equal to 192. Lesser of these two values should be taken. Okay, by assuming the member is subjected to tension. Okay, so if it is subjected to compression, it will not be 16, this should be 12. Okay, once we have P minimum and P maximum, pick up a value, any value between those two. Okay, so in this case, I have picked up E equal to 33 millimeter and P equal to 50 itself. If you want to pick 55 millimeter, 60, 70, 80, that's fine, as long as that is less than 192 millimeter. Okay, this is the pitch. See, you may ask, why do we need the pitch value when we have only one bolt? But for calculation purpose, we need this. Okay, once we know E and once we know P, find out what is E by 3DO. DO is the diameter of the bolt hole. So I got 0.50. So again, P by 3DO minus 0.25. Where did we get all these four formulas? Again, page numbers 75, column 2. Okay, under 10.3.4. So P by 3DO minus 0.25 equal to 0.508. So FUB is the tensile strength of the bolt and FU is the tensile strength of the plate. That is equal to 0.975. And in any case, these three values should not exceed 1. So we have four values. Out of these four values, take the least one, which is 0.50. So that is the value of KB. Okay. So please substitute this value of KB in this formula, where VDPB equal to 2.5 KB dt FU divided by gamma MB. Okay. So when I substitute, so 2.50 multiplied by KB, what is KB? 0.50 multiplied by D is the diameter of the bolt. Okay. T is the thickness of the thinner plate here, because we have two plates of the same thickness. Okay. 12 millimeter is the thickness we are going to consider. Multiplied by FU value, that is 400. That means why I have taken 400? See here, when this bolt is pressing against the plate, that is two materials are pressing against each other, and if those two materials of different strengths, so which one will yield first or which one will fail first? The material having lesser strength, is it not? So in this case, bolt has a strength of 400 Newton per millimeter square and the plate has a strength of 410 Newton per millimeter square. So out of these two values, 400 is the lesser value. That is the reason why I have considered 400 Newton per millimeter square in this formula to find out what is VDPB. So what is the value of VDPB? That is the bolt strength in bearing. Okay, VDPB is the bolt strength in bearing, I repeat. So I got that value equal to 96,000 Newton. That is equal to 96 kilonewton. So as I said, a bolt can fail in two possible ways. One is through shear and the other is through bearing. So if at all it fails due to shear, it will fail at 45.26 kilonewton external force P. If at all it fails due to bearing, it fails at P equal to 96 kilonewton. So out of these two values, out of 96 kilonewton and 45.26 kilonewton, so lesser value should be taken. So that is the design strength of the bolt. So I say design strength of the bolt or the bolt value. So this 96 kilonewton is the design strength of the bolt in bearing. Okay, 45.26 kilonewton is the design strength of the bolt in shear. So lesser of those two values is the design strength of the bolt itself. So another name for bolt design strength of the bolt is bolt value. In short, we are going to say, okay, what is a bolt value? We say the bolt value is 45.26 kilonewton. Okay, so that is the first case. Next, so if you go to the problem once again at the top, it says second case, that is single cover butt joint, the cover plates being 10 mm thick. So see, single cover butt joint, the cover plates being 10 mm thick. So these two are the plates of 12 mm thick. Okay. So butt joint means they are coming face to face, those two plates. So they need to be connected. So we are connecting them using a cover plate. So what is the thickness of the cover plate? 10 mm thick. So for analysis purpose, so P is the force to which this joint is subjected to. For analysis purpose, what we do is we are going to consider only half of this joint. Okay, the same thing we are going to replicate on the other side. Okay, so then here the bolt is in single shear. Forget about this side, only 50% of this side for analysis purpose. So the bolt is in single shear. So what is the design strength of the bolt in single shear? It is 45.26 kilonewton. We calculated that value already, so we don't have to repeat it. Next, when it comes to bearing, see here KB value is the same. Okay, so that is 0.50 we already calculated. D is the diameter of the bolt. Please hold on for a second. Sorry. Okay. So when it comes to bearing, okay, when you pull these two plates, so you are going to transfer the force through this cover plate. Okay. So it is as good as when you pull this plate by a force P, and this cover plate is also going to be subjected to the same force P. Okay, it is like a lap joint. It is like a lap joint of two plates of two different thicknesses. So one is 10 mm and the other is 12 mm. Okay, so here when you pull it, this surface, this side gets stressed, and when it comes to the cover plate, this side gets stressed. Okay, so if you keep pulling it, if at all the bolt fails by bearing, actually this plate fails because this plate and this plate are transferring the same force because of less thickness, that is 10 mm thickness when compared to 12. So this plate fails first because the stress is more here. So that's why when you find out the bearing value of a bolt, we should consider the thickness lesser of these two plates, which is 10 millimeter. So that's why if you look at this formula, okay, 2.5 kb 0.5, d is the diameter of the bolt, t is the thickness of the thinner plate. Here I am not substituting 12 mm thick, instead I am substituting 10 mm thick cover plate multiplied by 400. 400 is the bolt tensile strength. Okay, multiply, divide that value by 1.05, again by 1000 to convert the value into kilonewton. So what is the bearing value of the bolt? That is VDPB, that is equal to 80 kilonewton. Whatever value you find out here is always per bolt. Okay, so we have shear value 45.26. Okay, we have bearing value 80 kilonewton. So out of these two values, take lesser value, which is 45.26 kilonewton. That is the design strength of the bolt, or in other words, that is the bolt value. Okay, is it clear to you? Next, third case is double cover butt joint, each of the cover plate being 10 mm thick. So here again, these two are the main plates. Okay, and these two are the cover plates. So what is the thickness of each plate? It is 10 mm. So in this case, it is single cover. So in this case, it is double cover butt joint. So if you look here, so how many shear planes we have? So when you pull this, if at all the bolt fails due to shear, so it fails along two planes. Okay, that's why in this case, the bolt is in double shear. And by assuming that both the shear planes are passing through the threaded area, so if you look at this formula, Fu by root 3 multiplied by Nn ANB plus Ns ASB, go to page number 75, 10.3.3. If you go to page number 75, 10.3.3, there you'd see VNS equal to Fu by root 3 Nn ANB plus Ns ASB. In this case, we are going to assume that all the shear planes are passing through the threaded area. That way, Ns equal to 0. That is number of planes passing through the shank equal to 0. Then when we come to Nn ANB, Nn is the net area, that is number of areas passing through the thread. So in this case, because the bolt is in double shear, Nn equal to 2 and ANB is the bolt area at the threaded section. That's why I have written only Nn ANB plus Ns ASB. I have taken that as 0. So Nn is 2 because the bolt is in double shear and all the shear planes are assumed to be passing through the threaded area. And of course, this is the net area, 245, pi by 4 multiplied by 20 square multiplied by 0.78. Okay, so 400 by root 3, this is VDSP, that is the shear strength of the bolt. When the bolt was in single shear, the strength was 45.26. Because the bolt is in double shear, the strength gets double. It is 90.53 kilonewton. Okay. So when it comes to bearing, here, as I said, so we need to consider only 50%, not this 50%, any 50%. So if you apply P, so the load gets transferred from one side to another through these two plates, is it not? So if you apply a pull here, so this side gets pressed, okay? And this side for the cover plates, okay? Not this side and this side for the cover plates, okay? So in this case, when you come to bearing, VDPB equal to 2.5 kb dt Fu divided by gamma mb, 2.5 multiplied by 0.5, we calculated 0.5 already. D is the diameter of the bolt, 20, and T is 12 millimeter. So see, this is very important. So if you understand the concept here, so it is going to be easy for you. Look here. So this plate is 10 mm thick. This plate is 10 mm thick. This plate is 12 mm thick. So in the previous case, I said, so take the thickness of the plate, which is lesser in value. That's why I took 10 mm thick plate in case of the previous example in single cover butt joint. Okay. But in this case, this side is getting stressed, and in this case, this side and this side of these two cover plates are getting stressed. So that means these two cover plates are acting together, and this plate, the main plate, is acting alone. Okay. So what we must do is we must add the thickness of this cover plate with the thickness of this. And in this case, it is 20, 10 plus 10, 20. That should be compared with the thickness of this plate, which is 12 millimeter. Lesser of those two values should be taken. If at all the bolt fails by bearing, this is where it fails. Okay. These two combined thickness of 20 millimeter is greater than the thickness of the plate, which is 12 millimeter. So lesser value should be taken. So that's why I have taken 12 millimeter in this case. So once you do this, so VDPB, that is the bolt strength in bearing, is 96 kilonewton. Okay. So now have two values, shear value and the bearing value. Therefore, the design strength of the bolt or bolt value is 90.53 kilonewton, which is lesser of these two values. Hope this is clear to you. Anyway, you have the notes, guys. Take a printout of it. So please go through it once. Okay. And if you get any doubt, anytime, okay, on anything, please get in touch with me. So as soon as today's classes are over, so spend some time on this. So once you start learning this, it will not be difficult for you. So if you pile up everything until the last day of the examination, then it is going to be, very, very difficult to understand and pass this subject. So only through constant studying and understanding and through getting your doubts clarified, so you can enjoy this subject. Otherwise, it is going to be really difficult for you guys. Okay. So this is the next problem. So in the next 5 minutes, I don't think I can cover this part. So what I do is I'm going to end this problem in this class. So I'm going to start with the next problem in the next class. Okay. So please get ready for the next class. Good luck, guys, and stay safe. Okay. You can drop off. Thank you.
Thank you, sir.